Welcome to the LPI virtual seminar this week. Thank you all for coming. Our guest this week is Scott Guzewich of the NASA Goddard Space Flight Center. Scott is a research astrophysicist there. He got his degree from Johns Hopkins in 2013, and since 2016 has been a participating scientist on the MSL mission in Mars Science Laboratory. His talk today will be on volcanic climate warning and the implications for terrestrial habitability. Just as a reminder, please make sure your microphones are muted during the talk. If you have a question during the talk, please feel free to type it into the chat. We'll address them in the last 15 minutes of the hour. If you would like to ask a question of Scott directly, then let us know, and we will ask you to unmute your microphone. Outside of that, thanks for coming, Scott. Please take it away.
All right, yeah. Thanks, Sean, for inviting me, and Debbie for coordinating. I'm really glad to be here and share some of my most recent work about volcanic climate warming and the implications for terrestrial planet habitability. So I'm from NASA's Goddard Space Flight Center, as Sean mentioned. Want to mention funding source for this is what we call at Goddard the Sellers Exoplanet Environments Collaboration. This is a internal scientist funding model, so maybe you've heard that term in the ROSES conversations or that sort of thing here lately. As RNA programs have been changing, this is sort of a way that headquarters is funding NASA centers directly for certain projects. So SEEK, as we call it, is one of them. And I also want to thank my collaborators, Luke Oman, Patrick Welly, Jacob Richardson, Jake Bleacher, Kelsey Young, Ravi Koparapu, Sandra Bastelberger, and Thomas Fauché. So a long list of characters who've helped me do this work. So I want to make sure I acknowledge them as well. So I want to first just draw your attention to the picture I have here on the opening slide, because I think it's going to be relevant later. So this is from Eastern Washington State, and this is a picture of the Columbia River flood basalt terrain out there. And it has these very distinctive layers of basalt that have been in place over all these different volcanic flows that occurred over perhaps thousands or even millions of years. And I want you to kind of keep that structure in your mind if you're not familiar with it, if you're not a geologist like I'm not. But you're going to see a picture very much like that in a few minutes, and I want to make sure you remember it. So again, that's from Eastern Washington State, and you'll see something in a very different place that looks a lot like it soon. So if any of you are going to do email or or otherwise be distracted for the rest of the talk, I want to put my takeaway messages up front here, so you kind of get the main points, just as we read the abstract and conclusions in papers, so I'm going to give you the main points here up front, so you have them as we move forward. So a few things first. So climate cooling that occurs after a volcanic eruption because of the thick sulfate aerosol layer that can form. So this is much like what happened after the Pinatubo eruption back 30 years ago, where this massive eruption occurred in the Philippines, and the sulfur dioxide was chemically converted to sulfate aerosols in the stratosphere, and those are very bright, and they reflected sunlight coming into the planet and actually cooled the planet by a degree or two for a couple of years. But what we find is that even with a massive eruption, which we simulated here, which is much, much larger than Pinatubo, the cooling from that is very, very short-lived. What in fact happens is dramatic climate warming, and this is not from carbon dioxide. This is a dynamical response and a radiative response to the sulfur dioxide, and is ultimately driven by this massive increase in stratospheric water vapor. And I'm going to speak a lot more about that later, but that's where really this comes from. But despite all of that, and this is some really radical climate shifts that happen over a couple of decades, the climate returns to normal after about 20 years. So it's not that long of a duration, even with a really major eruption here that we're trying to simulate. And so my point here is that the volcanic winter paradigm, where we've often thought in the scientific community that these really huge eruptions, these sort of flood basalt eruptions, probably created this very long duration cold volcanic winter, perhaps with glaciations, perhaps with long decades or centuries of very reduced sunlight. probably needs revision. And so I'll speak more about this as we go forward. So the motivation for this work ultimately kind of comes from trying to understand how flood basalt eruptions, which are very distinct phenomenologically from the sort of classic, stratovolcanoes, those big giant cones, like your Pinatubo's, like your Mount St. Helens, Toba, Tambora, these big eruptions that, ultimately only last a few days or perhaps, a week or two. How are they different when you have a flood basalt eruption which lasts for, years or centuries or millennia potentially? And how does the climate impacts differ when you have that super long duration of eruptions versus a one really punctuated shock like the stratovolcanoes can produce? And then, how does habitability vary? How does the response of a planet's climate change, based on these different stratovolcanic eruptions and based on the planet themselves? Could the habitability of a planet like Mars be increased? If you're starting from a colder, drier state, could you increase the habitability there? Whereas in a place like Venus or Earth, where you're already, warmer and wetter potentially, could you kind of push yourself away from habitability in those cases, and make the planet less habitable? And then, because our, SEEK, as I said, our funding source is ultimately looking at exoplanets and terrestrial planet habitability, across the universe, can you maybe detect these eruptions across light years? If you have this major disruption to the climate and you're watching a planet through, transit spectroscopy or perhaps even direct light imaging of a terrestrial exoplanet, can you detect these and see this, massive change to the climate and this change to the reflection spectra, this change to the transit spectra that such an eruption could potentially produce? So that's kind of where we came from with this work. So I want to also then speak, kind of give an introduction here about what flood basalt eruptions are and why they're maybe really interesting and distinct from the kind of eruptions that we're more familiar with, kind of in our lifetimes and in modern history. So these are, really high volume and long duration volcanic eruptions. And by long duration, we're talking perhaps tens of thousands of years. We don't actually know, we have no sort of modern reference for eruptions that last, thousands of years. You have your Kilauea type eruptions that are sort of slowly, effusive eruptions perhaps over decades, but at a really sort of low background level. And these flood basalt eruptions potentially are, much more voluminous, much more impactful, both locally and globally over a much longer period of time. And so they're very distinct. And they cover these vast areas with basalt. So we're talking, hundreds or even thousands of square kilometers. Some of these flood basalt eruptions are probably very familiar if you know anything about Earth history. So there's, hopefully you can see my cursor here, there's the Deccan eruptions that occurred, very much near the end of the Cretaceous period, near the end of the dinosaurs. And there's been this, ongoing debate for decades about whether it was an impact, the Chicxulub impact, or whether it was the Deccan eruptions that, really kind of sent the dinosaurs toward extinction. And that debate is not over. I mean, there was a paper, I think, in Nature just a couple of years ago suggesting that the Deccan eruptions were sort of supercharged by the shock that the Chicxulub impact might have had to the planet and the mantle, and would have increased the eruption outflow from Deccan and might have then kind of been another contributing factor to the extinction of the dinosaurs. There was the Siberian traps. This is the largest one, I believe, in Earth's history, at the end of the Permian. So this has been sort of possibly linked to the end, one of the greatest mass extinctions in Earth's history, the Permian extinction, end of the Permian extinction. And the one we're talking about here, in my talk, is the Columbia River flood basalt here, which is the most recent one, only about 15 to 17 million years ago. And it's here close to home in the Pacific Northwest. But you can see these have occurred, all over the planet, in the ocean basins and on the continents. And, they are contemporaneous with many or most, maybe even all of the mass extinction and ocean anoxic events in Earth's history. I'm an atmospheric scientist. I'm not a biologist. I'm not a geologist, but I can see, a line with a slope of 1 just as easy as any of you. And the connection here is certainly suggestive at the very least, So you can see some of the big ones here, like I said, the Siberian traps and the end of the Permian. The Central Atlantic Magmatic Province, the end of the Triassic was a major extinction. of course, Deccan and the end of the Cretaceous with the end of the dinosaurs. And then the one we're talking about down here, Columbia River flood basalt, which is actually one of the few that kind of falls a bit noticeably off that line, but still quite close to it at the in the Miocene. So you have this remarkable coincidental timing, contemporaneous timing between these eruptions and these major extinction events in Earth's history. So, at the very least, it seems more than a coincidence, and probably that these eruptions in some way alter the climate to such a degree that a lot of biological activity and different species and taxa were sent to extinction. And these are, eruptions are quite common in the solar system. They seem to be common to all terrestrial worlds in our solar system. We don't have as much data on Venus because of course, the challenges seeing its surface. But certainly the other three major terrestrial worlds in the solar system all have flood basalts. So as you will hopefully recall from that first slide of my presentation, and you saw those sort of very stacked layers in eastern Washington state from the Columbia River basalt eruption. Well, look here on Mars on the right side of the chart, and you see something that is all but identical looking, at least to my eye. Again, not a geologist, but they look all but identical to the same sort of features we saw in Washington state as those on Mars here. Obviously much more ancient on Mars, but it seems to be the same sort of feature producing these stacked columns of basalt. On the moon, the lunar mare, the dark features on the moon's surface, the seas of the moon's surface are believed to have formed by flooding basalt through very similar processes to the flood basalt eruptions on Earth. They've often been, kind of linked to that sort of feature on Earth, and they've covered these very vast arrays with relatively smooth plains from these volcanic eruptions. And then Jim Head and colleagues, found these features on Mercury with messenger data. Again, so it seems like all five of the major terrestrial worlds in our solar system have had flood basalts. Obviously, their compositions are all relatively the same, but it certainly suggests that terrestrial exoplanets, should they be made of similar stuff to our planets, that they would potentially also have major basaltic eruptions like this that could alter the climates of these planets. And how do those eruptions alter climates ultimately? And this is a nice cartoon I found that sort of hits the highlights, the high notes of how this works. So of course you have the volcanic eruption, and what can also happen is that you have these magma spreading and kind of spreading underground to reach nearby coal seams or shale that could sort of enhance the gas output from these events, increase the amount of carbon dioxide and sulfur dioxide and water vapor that these events otherwise would emit alone. So carbon dioxide is emitted, sulfur is emitted. The sulfur is quickly converted to sulfur aerosols, which again reflect incoming shortwave sunlight. And of course, the carbon dioxide acts to increase the greenhouse effect and warms the planet. It also then would increase, the weathering of the planet and help, bring nutrients and materials back into the ocean, acidify the ocean, and help create ocean anoxic events. So that's sort of the climate impacts in a nutshell. But they've never been, sort of comprehensively simulated in a sophisticated climate model. There have been a lot of aspects of this that are sort of independently done, but simulating the chemistry, simulating the cloud impacts, the precipitation, the ocean circulation, all together is something that hasn't been done, to my knowledge, for this degree of eruption. There's certainly been work on things like Pinatubo and even Toba or Tambora-sized eruptions, but nothing kind of the duration that a flood basalt eruption could produce with the volume of material that it could emit into the atmosphere. And so that's where our work really comes in here, and to see how those impacts are different. And the debate on whether these sort of eruptions produce cooling or warming is really still ongoing in the literature, and it's really fascinating to read, as a matter of fact, just sort of how different the takes are between different groups of scientists as to how the response to the climate ultimately results. So you have papers by Stephen Self and colleagues suggesting that the atmospheric cooling from the SO2 emissions of just one flood basalt eruption was likely to have been severe. So severe cooling from sulfur dioxide emissions. On the other hand, you'd have contact metamorphism. So that's sort of the, underground material, contacting coal and other materials that are rich in carbon dioxide. So you basically supercharge the emissions from the eruption, increasing the methane, carbon dioxide, and sulfur dioxide, which would cause intense global warming, because of course you'd increase these greenhouse gases and then cause major warming. Speaking about the Columbia River basalt eruption specifically, this paper by Kasbom and Schoen, which I'm going to reference again here, really tried to kind of narrow down that window of when they occurred, and put it in relation to what's termed the mid-Miocene climatic optimum. And I'm going to speak more about that here in a couple slides. But they then kind of narrowed that down and found that it seems to be overlapping, which would suggest that the eruption perhaps produced warming to produce this climate optimum, which was a warm period during the Miocene. But then Schmidt and colleagues also looked at the aerosol feedback from the sulfur and found that a Rosa scale eruption, so Rosa was one of the phases of the Columbia River eruption, would have produced a 3-degree cooling of the planet due to the sulfur cooling, sulfur aerosol cooling, and a larger eruption like Deccan would have produced 4.5 degrees. So this debate kind of constantly has been going back and forth in the literature, and is still going on today. And there's this, people focusing on the sulfate aerosols have suggested severe cooling. People focusing on the carbon dioxide emissions have suggested that would cause warming. And so, you got to kind of see how that synthesizes and gets put together. So Columbia River basalt specifically, it's of course in the Pacific Northwest, Eastern Washington State, and Oregon primarily. And it occurred over, a variety of different phases, and probably over perhaps as much as 2 million years. The Grand Ronde was sort of the largest member, and we're going to simulate an aspect of the Grand Ronde called the Wapshiller Ridge member. But you can see it's 70-some% of all the basalt that was emitted was during that particular phase. But the duration of any individual eruption over this 2 million years was perhaps just a few years, where a lot of magma was emitted, a lot of basalt was emplaced. And despite all of that, this was relatively a small flood basalt by Earth's history. Some of these other ones were much larger in terms of volume and area. And geologically, it's the most recent. Again, most of these other ones are quite distant in the past. And there's this compelling connection to the mid-Miocene climatic optimum. So this figure on the left here is from Jim Hansen, and it kind of shows how the climate evolved over the last 65 million years, essentially from the end of the dinosaurs at the end of the Cretaceous. And as you may have heard, if not, there was this what's called the PETM, the Paleocene-Eocene thermal maximum. This is sort of the warmest period in sort of the modern Earth history since at least the dinosaurs, if not before. And it was quite a bit warmer than modern Earth today. But then after that, there was a sort of steady cooling of the climate and sort of the beginning of the Antarctic glaciations around 35 million years ago. And then there was this kind of brief period here around 15 million years ago, 15 to 17 million years ago, where the planet seemed to warm, perhaps by 1 to 7 degrees Celsius with some regional variations. And the Antarctic ice sheet was partially deglaciated again. And so this is termed the mid-Miocene climate optimum. But after that, there was this general cooling trend again that kind of resumed. The northern hemisphere began to glaciate, Greenland, the Arctic began to glaciate, and you got sort of a general cooling as it continued toward the modern era. And so how the Columbia River basalt eruption kind of fit into this brief warm period followed by a cooling trend has been what the literature has been discussing for decades, really. There's evidence that CO2 emissions probably increased atmospheric levels to around 400 to 500 ppm. So for reference, right now we have caused our atmospheric CO2 levels to reach about 410 ppm. So we're kind of getting in that range. Before that kind of peak in CO2, there was lower levels, probably in the 200 to 300 range, more like a pre-industrial level. And then again, afterwards, there seemed to be lower CO2 levels. CO2 was drawn back down into the atmosphere and the crust. And so the question is, okay, did the eruption release all this CO2 and cause this, this warm period, Or did the sulfur dioxide emissions and the associated aerosols end up cooling the planet and kind of initiate that reglaciation and that cooling trend that prevailed towards the modern era? And so that's kind of where the timing of the Columbia River basalt eruption relative to this climate optimum and then the cooling trend afterwards is really critical to understand. And then, this aspect here is I'm kind of speaking now both about Columbia River and our simulation methods, is that, the mid-Miocene 15 million years ago was not a perfectly modern Earth. There were subtle differences, but very important ones. And the most important one is the Panama problem. So the Isthmus of Panama has been sort of steadily closing over this period from about 20 to maybe 2.5 million years ago. And, how that precise timing and when that precisely occurred and sort of how it occurred is really critical to understanding the climate during this period. The eruption likely occurred with the isthmus open. And having that open isthmus really changes the climate of the planet and changes the ocean circulation dramatically, because having that sort of tropical connection between the Pacific and the Atlantic and that east-west flow between them really makes the Atlantic mean overturning circulation, the AMOC, really different. Once that closed, the AMOC was really established and sort of altered the heat transport poleward pretty significantly, it seems like, based on paleoclimate studies. And there's some evidence that maybe the isthmus was sort of closing slowly. The way that they get this timing is actually by looking at fossils of different plant and animal species, kind of in North America, Central America, and then in South America, and seeing when this particular shrew from Central America showed up in fossil records in South America. And that suggests that, it just walked across the isthmus. So the isthmus must have been there by the time that this fossil was laid down. That's not really perfect because, animals and plants can move across water on rafts and swim. And there was suggestion that there was probably islands, kind of where the isthmus is now. So they could maybe island hop, across. And so the timing is not exactly known. And it might not have actually taken the full closure to kind of change that ocean circulation either. So there's a lot of really subtle details in there, and it's really fascinating as an independent science question, but it's not one that we wanted to deal with. So, we're simulating the eruption with completely modern topography. And, just as a kind of overly honest method here, it also makes it way easier to do. The model that we're using, GEOS-5, the GEOS chemistry climate model, is designed to do modern Earth climate problems. And although perhaps it is adaptable to do, this sort of paleoclimate question, this different topography means, you have to have a different, boundary condition file. And then you need to kind of create a different ocean topography, and bathymetry file. And then you need to sort of spin up the ocean with that different bathymetry and that different continental configuration. And so there's a lot of work that would need to be done, work that is beyond the scope of our problem to understand that and to really kind of exactly try and replicate the Miocene climate and the response of the Miocene climate to the Columbia River basalt eruption. So we didn't want to do that. We're just looking at sort of, the general climate impacts of these sort of eruptions, not specifically addressing Columbia River and the Miocene climate, although those are both very interesting questions. And there's some other really important changes too. Note that the Arctic was almost completely closed. You only have this very narrow sea lane kind of between Greenland and Russia that was open. Otherwise, the Arctic was basically completely enclosed, including here, kind of Beringia, Alaska, and then between Greenland and Canada. You also don't have the Red Sea, and you also have, perhaps the Persian Gulf and the Mediterranean connected. So you have water flow between the Indian Ocean and the Mediterranean. And then, as I mentioned earlier, Antarctica was partially deglaciated during this period. And so, understanding the exact Antarctic topography and the land mass of surface ice is something that is unknown and an area of active research. So how do you actually, simulate this sort of eruption in a climate model? So we take the Goddard GEOS chemistry climate model, and just sort of, if you're not a climate modeler or an atmospheric modeler, these sort of are ultimately modular systems. So you have this umbrella model, and then within it, you have these different components. So first and most important for any atmospheric model are what's called the dynamical cores. So basically these do the physics of atmospheric motion and fluid motion in the atmosphere and the ocean. So they do the transport, they do the advection, they do the physics of vorticity and spin. They take care of all of that atmospheric physics. That's what the dynamical cores do, and those are obviously critical to any atmospheric model. You have the radiative transfer, so that's, you know, taking sunlight in, understanding how infrared radiation moves through the system as it is reflected and emitted by clouds and atmospheric gases and things like that. In our model, which is really critical, is that we have, you know, chemistry and aerosol modules. And a lot of, you know, so planetary models like I use for Mars, oftentimes, these are rather limited or non-existent, particularly the chemistry. You know, a lot of models don't actively simulate the chemistry because it's very computationally expensive to do so. So this model is actively, you know, following the chemistry of the atmosphere and doing chemical reactions at the same time that it's doing the atmospheric physics. And again, most don't do that. And of course, clouds are also, you know, interfaced with there. Cloud formation is very responsive to atmospheric aerosols and atmospheric chemistry. And so the cloud physics goes in there as well. And then of course you need some sort of initial and boundary conditions, you know, where you start, you know, where's your ocean state, where's your atmosphere state, and then you start the model from that point of view. And within those boundary conditions, you know, that's the atmosphere and the ocean. We're using pre-industrial chemistry, as I mentioned. So we have 280 parts per million of carbon dioxide, for example, and that is fixed in the model. We're not changing that. The eruption does not change the carbon dioxide in the atmosphere. You know, there's things like, you know, there's no anthropogenic chlorine, there's no CFCs in the model because we're using a pre-industrial atmosphere. But again, as I mentioned a couple slides ago, we are going to use modern surface conditions, you know, modern topography, modern solar forcing, although that's not going to be very different 15 million years ago. And then what our model then needs is a volcanic eruption scenario. So we need to know how much gas is being emitted in the atmosphere, where it's being emitted, and over what sort of cadence is it being emitted. And that's the scenario. And so there's a few aspects that go into that. So first is, you know, how much mass of sulfur dioxide are we going to put into the atmosphere? And so, you know, we're doing this based off of, you know, the best estimates by the literature. So Davis and colleagues in 2017 has suggested that as much as 300 gigatons of sulfur dioxide was emitted by the Wapshilla Ridge member. So that's kind of where we started off. And we tried to simulate 300 gigaton emission, and that did not work. The model chemistry just could not handle that much. We just got, you know, out of bounds chemistry module errors, and the model crashed. So we scaled it by 1/10 for a 30 gigaton total eruption. And the model could handle that and do that, and that's still an extremely massive eruption. So for scale, you know, this is a couple thousand times Pinatubo, for example. So Lori Glaze, you know, the head of our planetary science division at NASA, has done a lot of work on this as well. And so she looked at the Rosa member of the Columbia River basalt eruption, kind of looking at how the eruption was a mix of these explosive, you know, think more Pinatubo, eruptions where you're emitting material well up into the troposphere and into the stratosphere. You know, you have that huge sort of classic volcanic column. And, you know, and then an effusive eruption where you have just sort of near surface sort of emission of gas and material. So think more like Kilauea, where you have kind of a low grade, steady eruption near the surface. And so, you know, Lori's work suggests that this was, you know, kind of a balance between these two of some mix, where you have these huge perturbations, these huge emissions well up into the atmosphere with a constant sort of near surface background occurring at the same time. And so that's what our scenario ended up using. And then back to Davis, which suggested, you know, perhaps as few as 3 to 4 years to emplace the Wapshilla Ridge. So that's a huge amount of material over 3 to 4 years, but maybe extending as long as 94,000 years. We cannot run a simulation for anywhere near that length. So we put everything into 4 years, and that's where our scenario came up with. So we have 30 gigatons of sulfur dioxide over 4 years, and an 80% explosive, 20% effusive mix. So that's the scenario we gave to the model, and let that run and see how the climate responds. So what does that do? Oh, and a couple really important notes here before I show the results. So SO2, sulfur dioxide, is not radiatively active in the model. Sulfur dioxide is a greenhouse gas. It does warm the climate. It is very rapidly converted to sulfate aerosol, as I've mentioned, but we do not have sulfur dioxide radiatively active in the model. So it is just completely neutral as far as radio transfer is carrying. As I mentioned a couple of times, we fixed the carbon dioxide. And we also, importantly, did not emit any additional water into the atmosphere. So all the water that kind of the simulation starts with is what the simulation ends with. Water is conserved in the simulation. It's in the oceans, it's in the rivers, in the lakes, it's in the atmosphere in terms of water vapor. And the model is just moving that around between those different reservoirs. It's not adding any from the eruption or from any other source. So what does this eruption do to the planet and to the climate? And it's a bad few years for planet Earth. So this figure here on the left is just mixing ratios of sulfur dioxide and sulfate aerosol. And as a function of pressure, that's our vertical coordinate in atmospheric science. And that's a log scale. So the surface, 100 millibar or 1,000 millibars, going up into the mesosphere at around 10 millibars. And then this is kind of a cross longitude here. So kind of a loop around the world at the latitude of Columbia River. And, so sulfur dioxide is normally a part per billion level trace gas on Earth. And even the cloud tops of Venus have hundreds of ppb at most. And our simulation produces, ppm, parts per million level or higher but dioxide in the atmosphere. So you would smell this, if you were standing out there anywhere kind of near the surface, particularly in North America, but maybe even anywhere else, you would smell the sulfur in the air. Because it would be extremely high concentrations relative to normal. This figure here also kind of neatly shows that split between explosive and effusive eruptions, as I mentioned before. So here's the explosive eruptions emitting material high up in the atmosphere, in the top of the troposphere and the lower stratosphere, and you can see that spreads out downwind toward the east. And then there's also material here being emitted near the surface, which is then being mixed a bit vertically, but also spreads downwind toward the east. And then 4 years later, at the end of the eruption, you have this very kind of globally fairly uniform layer of sulfate aerosol. So this is bad news for Earth's climate and anybody living there at the time. The sulfate aerosol layer becomes so thick that global area-weighted opacities exceed 200. So this is really, really, really high. Aerosol optical thickness, tau, as we say in the Mars community, when we talk about dust in the atmosphere, we often use the word tau. So maybe you're familiar with that term if you are a Martian scientist in any way. But this is really, really high. Oftentimes, from, let's say, wildfire smoke, that's something that a lot of us are familiar with in the United States recently, with all the fires out west and in Canada. You can get aerosol optical thicknesses of 1, maybe even a little more than 1 sometimes, well away from where the fires are. Obviously near the fires it's much higher, but last year here around DC and Baltimore, when all those fires were occurring out west, we had aerosol optical thickness smoke of about 1 or 1.5, which is quite high. And you can notice that, the sun looks redder, there's kind of a haze in the sky, and you often get, something like that for pollution as well. And here we're talking about 200. And this is, again, a logarithmic scale. So it's not linear. And you can see how this spreads out here on the animation on the right. It's concentrated in the northern hemisphere where the eruption is, but through the circulation and through diffusion, it does spread into the southern hemisphere as well, and still at very thick levels. This is at 125 millibars. This is well up into the stratosphere, kind of where that aerosol layer is most thick. And just for reference again, to make this maybe a little more familiar, so during the Mars global dust storm 3 years ago, 2018, that ultimately doomed the Opportunity rover, which was solar powered. The rover periodically every day took pictures of the sun to kind of monitor how much dust is in the atmosphere. It did this kind of for its entire mission to understand the solar power generation that it was doing. And so on the left there is a tau of 1, aerosol optical thickness of 1. And you can see the sun very brightly. It saturates the image, and it continues to saturate the image as you kind of go by factors of 2 here to darker and darker skies. On the right is where the rover ultimately met its fate with a tau of around 10 or 11. You could not see the sun. It was extremely dark at the surface. Surface illumination decreased by about 99%, and that's ultimately what doomed the rover. And so that's at 10 or 11, and we're talking here around the Earth of around 200. So very, very dark skies, not good for photosynthetic life forms. Speaking of not good, so the ozone layer is significantly destroyed and disrupted due to this. And we conducted a simulation with a post-industrial atmosphere, and we saw the same sort of thing, but we believed it was largely attributed to the presence of anthropogenic chlorine, which would accelerate this destruction in response to the eruption. But in this case, that's not present. So all of this is driven through dynamical changes. Basically, the stratospheric circulation is significantly perturbed. And that dramatically reduces the ozone in the atmosphere and destroys a lot of the ozone. The ozone loss is greater than the modern Antarctic ozone hole, and it's globally. So the modern Antarctic ozone hole is a reduction of around 100 to 150 Dobson units. That's kind of the measure we use for atmospheric ozone. And it's basically like sort of, if you took all the ozone and compressed it into one layer, how thick that is. And it's really quite thin, only a couple millimeters in the poles, but it's reduced significantly in the ozone hole. And here we have kind of global loss of around 200 Dobson units with maximum losses of 300 to 350 Dobson units. So significant reduction in ozone, not complete destruction, but significant reduction in ozone throughout the whole planet. And it's concentrated in the middle and the high latitudes. And so when we originally kind of started this project, we thought we were going to, as I mentioned, maybe kick off a glaciation event even, and sort of kickstart, a dramatic global cooling that would last for decades or maybe even longer. And within the first year, you do get a very significant cooling response to the eruption and to that thick sulfate aerosol layer, because you just don't have the sunlight reaching the surface. And you can see that on the animation on the right, where at the beginning of the year and as it progresses, particularly in summertime here, June, July, right now, August, you have this really intense cooling over the continental areas, particularly in the Northern Hemisphere. So you get cooling globally that averages about 5 degrees on an annual average basis. But over those summer continents, you're talking about coolings of 10, 20, even 30 degrees Celsius. So, take where I am here in DC, or where all of you are in Houston, where, mean summer temperature here in July, for example, for me is probably somewhere around, 25, 27 degrees Celsius. For those of you down in Houston, probably a little bit warmer, maybe closer to, 29 or 30. And this would reduce that temperature by, 10 to 20 degrees. So the mean monthly temperature where I am would be, around 5 to 10 degrees Celsius, in the 40s Fahrenheit, and maybe not much warmer than that in Houston. So this is a really dramatic change, but it only lasts for about a year, and then it quickly starts warming up. And you can see that clearly here on the left, where you see that very strong cooling, but then it steadily warms over the first 4 or 5 years or so until it pretty much gets back to normal by the end of the eruption. The end of the eruption is pretty much right here, 48 months, 4 years. And the temperature globally is back to normal. But note here that we have very opposite seasonality, where summer is actually the coolest time of the year, and then you actually get kind of winter warming. And this is something that previous studies of volcanic eruptions have seen, where you get this opposite seasonality. So that's kind of gratifying to us when we were doing the work, that we saw that same sort of response, but with this sort of background slope upward to warmer temperatures. So that cooling doesn't last long. And then what is followed by is really dramatic warming. And so as soon as the simulation is done, and the eruption is over, the climate begins to warm or continues to warm, and it ultimately peaks about 3 to 5 years after the eruption ends. And what's critical here is the timing. So the sulfate aerosol layer has now completely been removed by this point. And so you have all that sunlight coming back down to the surface. And there's this major response that I'm going to speak about here in a few minutes about stratospheric water vapor. And you get this really intense warming. So we've gone from a sort of a summertime temperature change of 10 to 20 degrees colder than normal, the difference between a baseline simulation, that it does not have the eruption, to perhaps 10 to 20 degrees of warming. So like a 40°C swing over some of the continental areas in the northern hemisphere. Really, really dramatic over a relatively short time, within a decade. And so that warming peaks after the eruption ends, and then has a very kind of slow decay time scale as the simulation progresses onward. And what this is really due to is stratospheric water vapor. The tropopause is completely lost during the eruption. So this is the cold trap in the atmosphere. This tropical tropopause prevents water vapor from getting up into the stratosphere. And the eruption, the eruption basically removes that entirely. And so water vapor can just flood into the stratosphere. Stratospheric water vapor goes from, ppm level, which is normal, up to part per thousand level. So this is really dramatic. And it increases this long wave infrared flux down to the surface by 50 watts per meter squared. So the perturbation to the long wave flux by climate change is only a couple watts per meter squared by the additional carbon dioxide. Here we're talking 50 watts per meter squared. So order of magnitude plus more from the stratospheric water vapor. And this just radically alters the climate so significantly by having all this water vapor up in high altitudes. There's some interesting, perhaps, implications also for water loss on planets like Venus and Mars because of this, but that's beyond the scope of our study. So despite that radical change, within 15 or 20 years, we kind of get back to normal. The ozone layer largely recovers with maybe some kind of perturbations and variations regionally, but for the most part gets back to normal. And the temperature here gets back to normal after about 20 years. We kind of fall back on top of that curve and we get back to normal temperatures. But it takes a couple of decades from the beginning of the eruption. So maybe 15 to 16 years after the eruption ends before we get back to normal. But it does get back to normal. We don't push the climate kind of to a tipping point where it goes off in one direction. It sort of does return to that baseline normal after a certain amount of time, and even after that really major eruption. So the climate response is transient to this. So concluding thoughts here, now that I got about 15 minutes before, and so I want to leave time for questions. This is the same slide I put up in the beginning. So climate cooling from the sulfate aerosols is really very transient. What ultimately happens is we get massive climate warming because of this stratospheric water vapor increase. So flooding of the stratosphere by water vapor produces this huge infrared flux down to the surface and warms the climate for several years after the eruption ends. But despite that, that all kind of settles back to normal with time, and the climate can return to normal after a couple decades. And so what I mean here by that paradigm needing revision is that you cannot get climate cooling over a long period of time from sulfate aerosols. They're just removed far too rapidly. And having this climate model that has the chemistry and has the aerosol physics all linked together, we kind of show this really well, that you can't keep the aerosols up there very long. They're just too big. They rain out, and you have all that water vapor up there that kind of can glom onto them as water droplets, and those are all removed very quickly, even for these huge massive eruptions. And so the dynamical response and the water vapor response, that's what lasts longer. There's been a lot of times in Earth's past where there's these hyperthermal, very warm periods that are associated with past volcanic eruptions, and these are sort of believed to have been due to carbon dioxide release. But it seems maybe that's not entirely true. On short time scales, kind of immediately with the eruptions, it seems perhaps that the dynamical and radiative changes from sulfur dioxide may be just as important, if not more important. Maybe kind of sulfur dioxide is the short, sharp shock that kind of hits immediately, and then the carbon dioxide is sort of the long, long duration response, because that lasts much longer in the atmosphere, obviously. Centuries, millennia, or even millions of years before carbon dioxide is removed. And then here to just my last slide, this is some just, hand-waving speculation. What does this imply for other terrestrial planets? Could this have produced transient warming on early Mars? We seem to think now that the warm, wet periods on early Mars, if they did exist, were probably the exception, not the rule. Early Mars probably was cold for most of the time, but there obviously were times when liquid water could flow on the surface. And could those have been, brief periods, centuries perhaps, when you had these major eruptions, and you could have warmed the planet enough to have periods of rainfall, periods of erosion, that then kind of cooled back down to this dry, cold normal before the next eruption occurred, perhaps millions of years later. And then kind of on the flip side, could you have had these push Venus over the edge into a moist greenhouse or a runaway greenhouse? As I mentioned, all that water vapor flooding into the stratosphere, would have make things much more likely to escape to space, where water can be photolyzed at high altitudes, and then the hydrogen can be lost to space. And so could these major eruptions have, tipped Venus over to the edge where it lost water and where it was sent into a runaway greenhouse? So that is it for me. Thank you for your attention. And I hope there's some questions. I'd be happy to answer.
Thank you so much, Scott. That was great. That was a really great talk. I know it's hard sometimes to get a sense for the audience appreciation in these virtual things. If you enjoyed the talk, please let Scott know in the chat. We would appreciate that. Yeah, if you have any questions, please type them in the chat, or if you'd like to ask them directly, you can ask to unmute. We've got one right away. Tyler and Palladino asks, where does your assumption of 80% explosive to 20% effusive come from? Given that volatile species being present in the stratosphere is important for altering the climate, are your results significantly different if you vary the proportion of explosive to effusive eruptions?
Yeah, that's a great question, Tyler. And that's actually one that we are going to address with our follow-on project that was just selected for funding. But so the 80-20 mix comes from some of Lori Glaze's work, looking at the Rosa eruption, one of the Columbia River basalt eruption members. So we're kind of getting that from Lori's work and others, which I've kind of tried to tease this out and see where the difference would occur. It seems that the effusive eruptions in general are just going to be sort of, less material because they're sort of, just less intense. There's less pressure being built up below, and so they're kind of less intense, and so less material is emitted anyway. And then there's these huge explosive eruptions which can emit much more material over short periods of time. And so that's kind of where that balance comes from. And, but we had the exact same question about, how sensitive are the results if we are not putting the material directly up into the stratosphere? And so our follow-on project is going to look at that directly and try and do the same sort of simulation, but emit all the material near the surface instead of up in the troposphere, on the upper troposphere and lower stratosphere. And, I suspect that if you do that and you don't emit it directly up into the stratosphere where those sulfate aerosols are most effective and impactful for the climate, that you probably wouldn't get the same climate response. But I don't know exactly what that climate response is going to be because we're going to do those simulations in the years ahead. But that's something I wanted to know of as well. So I see a question from Tim about Martian volcanism. I couldn't know what the question is, Tim.
Yeah, I was going to ask for some clarification on that as well. Is that asking about the expected extent of Mars volcanism?
Yeah, I guess I'll say this. There certainly is evidence that Martian volcanism has continued into the Amazonian. So the Amazonian, for those who aren't Martians, is the modern era on Mars, which is the last 3 billion years. not entirely modern, but certainly. And my colleague Jacob Richardson actually just had a paper out on this, I think within the last year, looking at evidence that there was volcanism, I think on Tharsis, so that's the big volcanic province on Mars, even within the last 50,000 years. So there's still suggestion that Mars is not volcanically dead. But certainly, to my knowledge, all, the biggest eruptions, the most emplacement of materials was in the ancient past, in the Noachian and in the early Hesperian. So that's, maybe 3.5 to 4 billion years ago.
Do we have an idea of the pace of volcanism during the Hesperian and how that would relate to the time scale of warming?
I don't have a good sense for that. I'd be happy to hear something about that. Okay, oh, I see. Tim can't respond. Yeah. Yeah, I don't have a good sense for that. And, this is certainly, I would love to do the same sort of experiment with a climate model that can simulate Venus or Mars. The one that we're using here cannot do that. So I am on the team that's developed a different climate model called Rocky 3D. Maybe some of the folks in the audience have heard of it, but it's an adaptation of another NASA climate model to kind of generalize it for terrestrial exoplanets and other planets in our solar system. And so we've done work on that for early Mars. Actually, I just had a paper accepted about early Mars with that climate model called Rocky 3D. But it cannot do yet, it can't do the chemistry and the aerosol physics that you really need, I think, to understand this problem. We're working on it, but it's not ready yet. But when it is, I definitely want to try and do something like this with that climate model and see what Mars would, respond to.
Awesome. Yeah, I'm looking forward to that. Do we have any other questions from the audience? Give it another minute or two. Don't be shy.
Well, either I answered all the questions or just wasn't compelling.
I think that, yeah, I think this is really interesting, especially kind of looking at it from the, not necessarily just the planetary standpoint, but looking at how this affects our understanding of things like mass extinctions on Earth. Just like there's always this assumption that, okay, there's a volcanic winter and everything dies, but
right.
That may be a two-step process, or.
So that's one thing actually I was going to have a slide on, but it's really far out of my wheelhouse, the biological response to this. But there's some suggestion that when surface temperatures get too hot, obviously that's really bad for mammals, right? Mm-hmm. And I've seen sort of different marks on the wall for what that temperature is. Some people use the wet bulb temperatures. That's basically the wet bulb temperature sort of reflects how much moisture is in the air as well, and have suggested that somewhere between 33 to 35 degrees Celsius wet bulb temperatures are completely inhospitable to life or to mammals because mammals can't kind of cool to the atmosphere that way. And there are places in the simulation that get wet bulb temperatures up to like 33 degrees Celsius. So really, very abnormal for modern Earth. We also get, continental mean monthly temperatures of 40 degrees Celsius, which is, way higher than normal even today in places like the Sahara Desert or Arabia, or Australia. And so you get, really, really hot temperatures over the continental areas in summertime. And I can't speak to exactly how stressful that would be to biology, but I can't imagine it would be pleasant. And then, as I talked about the ozone layer and the sulfate aerosol layer, I don't have a feel quite for, the lack of sunlight at the surface obviously would be really bad for photosynthesis for several years, would really prevent it almost entirely, I would think. But at the same time, without the ozone layer, UV would be able to penetrate a little bit lower in the atmosphere, but I'm not quite sure yet if the sulfate aerosol layer would block some of that UV, or if the UV would still be able to penetrate down to the surface and cause additional problems that the ozone layer prevents. That's something I'm talking to some colleagues about right now, but I don't have an answer for yet.
That's really interesting. Yeah, I'm really looking forward to hearing more about that as things develop. I don't see any more questions in the chat, so I think we can go ahead and everybody thanks Scott. I think it was a really great talk. I really appreciate it. So the LPI virtual seminar will be going on a short break over the course of July. It turns out that it's hard to get people to come and give talks in the middle of the summer. But we will be returning in the first week of August, and we have a full slate of talks for August. So I will send out announcements when we return. Thank you again, everyone, for coming, and have a great day.
All right, thanks, Sean. Bye, everyone. Thank you.
Take care.